Here is the fourth structural design pattern. This one is called Decorator Pattern, and it is a pattern you use when you want to extend the functionality of a class, but without actually creating a subclass. I'll start with a quick summary of what we are trying to accomplish with this pattern. The Decorator pattern is a good choice when you are trying to accomplish the following. You want to attach additional functionality to an object dynamically. You are unable to use subclassing for extending the functionality. Okay, let's go through the points. So the key here is that you want to extend the functionality of an object. But for some reason or other, you are unable to use subclassing. So how would you do this? The solution is very similar to the composite pattern that we discussed in the previous lecture. We learned that in the composite pattern, a component consists of a nested tree structure of child components. Calling a method at the root of the tree automatically calls all child methods too. In the example, I showed you how you can use this pattern to represent an HTML document with nested tags and write a render method that produces the correct output. Now, the decorator pattern is very similar. Again, we have a nested structure of child objects, but now the original object is at the root of the tree, and the child objects are called decorator objects. The original objects and the decorators all share the same interface. Each method first calls its parent, which may either be another decorator or the original object, and then it performs additional functionality. By stacking objects in this manner, you can effectively add any kind of behavior to any object. Please note that this pattern allows for extra functionality to be added to a method, but you cannot add extra methods to an object. Each decorator shares the exact same interface with the original object. Also note that the original object is now hidden beneath layers of decorator objects. Trying to access the original object directly is no longer possible. The decorator pattern offers a number of benefits. First of all, the pattern allows you to enhance the functionality of a method in any object without having to use subclassing. This can be useful if you are unable to subclass the object, or when the method in question is not virtual. The nice thing about decorators is that they sidestep the multiple inheritance limitation in C#. Due to this limitation, you cannot inherit functionality from two or more base classes. A class can only ever have one superclass, but you can easily apply two or more decorators to an object. So in effect, decorators kind of act like interfaces with a default implementation. Finally, the pattern hides the original object beneath layers of decorators. This can be useful if your client will only call high-level methods and you want to hide the complexity of the decorators from view. Here is the UML diagram of the decorator pattern. At the top of the class hierarchy is the Components class. This is an abstract base class that defines the common interface for the original object and all decorators. In the diagram, the class has one single abstract method called operation. There are two subclasses derived from the component's base class. One is called concrete component, and this is our original object. This object contains the default functionality that we want to extend with decorators. And so, this class provides the default implementation for the operation method. The other subclass of the component's base class is called Decorator. This is an abstract class that acts as the base class for all decorators. Now, notice that this class has a protected field that holds a reference to another component. You initialize the decorator by calling its constructor and providing the referenced component as an argument. The class also implements the operation method by having it simply call the same operation method in the reference component. There are two subclasses derived from Decorator: Concrete Decorator A and Concrete Decorator B. Notice how they introduce extra functionality to the component. Concrete Decorator A adds an internal state, and Concrete Decorator B adds new behavior to the operation method. So here's what you do to put this pattern to work. You initialize a stack of decorators like this. Calling the operation method will first call the operation method of Concrete Decorator A, which will immediately delegate the call to Concrete Decorator B, which will again immediately delegate the call to Concrete Component. The Concrete Component will perform the default implementation, and then Concrete Decorator B gets a chance to perform additional work. And finally, Concrete Decorator A also gets a chance to perform additional work. I am going to demonstrate the decorator pattern with the following example. I am going to write software for a pizza restaurant. In a pizza restaurant, you always have a selection of standard pizzas: margherita, quattro stagioni, funghi, and so on. But you can also combine a pizza with extra toppings. You can add ham, salami, extra cheese, mushrooms, peppers, and so on. Now, to incorporate all of this in a single class hierarchy would be very difficult, because each topping can be combined with each pizza. I would have to add subclasses for every combination of pizza and topping, an impossible task. So, this is a perfect job for the decorator pattern. Instead of trying to put everything into a single class hierarchy, I am instead going to implement the pizza as components and the toppings as decorators. I will have an abstract component class called Pizza Element that implements a uniform API across all pizzas and toppings. I will also use a method called getPrice to calculate the price of the finished product. This method will be implemented in all objects, so that I can simply call getPrice on the final stack of decorators and components to get the price of the finished pizza. There's also a concrete component called pizza that defines one of the standard pizzas. And there are separate decorator classes for each topping. Each decorator modifies the getPrice method to add its surcharge to the price. So, here are the classes I'll implement the pattern with. Let's take a look at the code. Here is the component base class called pizza element. You can see that it is an abstract class with a single abstract method called getPrice, which returns the price of the pizza as a decimal value. So, this method is going to be implemented in all pizzas and all topping classes. Next are the concrete components. Take, for example, the margarita class. It implements the pattern for a standard margarita pizza, and you can see that the pizza costs $8. And here is the fungi pizza, which is slightly more expensive, at $10. And here is the pizza topping class, which acts as the base class for all decorators in this example. You can see the component reference here, implemented as a protected field. The class constructor initializes the field with this argument here. So, when you create a decorator, you always have to specify the parent object. The pizza topping class implements the getPrice method, and you can see here that it simply calls the getPrice method of the referenced component and returns that value. There is no additional functionality here. That will come in the concrete decorator classes. And here is a concrete decorator. The with extra ham class is a subclass of pizza topping and overrides the getPrice method. You can see that it calls the base implementation and then simply adds $1.50 to the price. This is the price of having extra ham on your pizza. And here is the with extra cheese class. And you can see that cheese is cheaper than ham, only $1. Okay, finally, let's look at the main program method. The code here uses a sequence of nested calls to set up a margarita pizza with extra ham and display the price. The next code fragment sets up a fungi pizza with extra ham and cheese and also displays the price. Let me run the program to find out what these pizzas will cost. I'm compiling the code now. And now I'm going to run it. Here we go. And there's our answer. A margarita pizza with extra ham costs $9.50, and a fungi with extra ham and cheese costs $12.50. Everything works. Here is a quick checklist you can use to implement the decorator pattern. First, make sure you need to add functionality to an existing class and that you cannot subclass that class. And that there is an interface that is common to all. Then create an abstract class with the lowest common denominator component interface. Derive the existing class from the component base class. Create an abstract decorator class that also derives from the component base class. Then define decorators for each additional piece of functionality. And finally, have the client define the type and ordering of the component and decorator objects. Here are some final comments. I have already mentioned the similarity between the composite and decorator patterns. In fact, you can view the decorator pattern as a composite with a single child at each level. However, a decorator is intended for adding additional functionality. It is not meant for object aggregation. Both the decorator and composite patterns have different but complementary intents. Consequently, you can actually combine the patterns. And in practice, you do often see the composite and decorator patterns together. Finally, remember the difference between the adapter, proxy, and decorator patterns. An adapter provides a different interface to each subject. A proxy provides the same interface. And a decorator provides an enhanced interface. Okay, here is a summary of all that we've learned in this lecture. The decorator pattern is a good choice when you want to attach additional functionality to an object dynamically, and you are unable to subclass the objects. The pattern treats components and decorators in exactly the same way. The pattern is ideal if you want to apply layers of enhancements to an object operation. You can combine the composite and decorator patterns.